We begin the kinetics chapter, chapter 14, by talking about how would we measure a reaction rate and what is it. So generally speaking, what happens in a reaction over time as far as the quantities of the substances? So reactants are going to decrease in the quantity of substance because as they're reacted away, they disappear. And for products, the number of products are going to slowly increase in quantity over time. At some point, the reaction stops, and that means that the concentrations stop changing. It could be because the reactants run out, or we'll learn soon that it could be because it reaches a state of equilibrium and the reaction stops proceeding. So when we see, we would see for a reactant, it should be decreasing, and then eventually at the end, it kind of gets to a flat. And then for the products, it'll be, did I say it the other way? So for the products, it would be increasing and then get to a flat point where it evens off. So how quickly those concentrations may change, it can vary. So they might change very quickly. It might be a fast rate of reaction, or it might be a very slow rate of reaction. And about studying is that idea of what's happening to the rate of reaction during the course of the reaction. So let's go over a couple conventions. When we use the brackets, bracket A, bracket means we're referring to concentration and molarity of whatever substance A is. So inside the brackets is some kind of chemical formula, and then it might be an ion, and then the brackets itself means the molarity of that substance. So if I had brackets with a nitrate in it, that means the molarity of the nitrate ion. If I put a little subscript with a number in it at the end, or T, it would be the molarity at a specific time. So the subscript here means like at 30 seconds, or it might say, sometimes we just say T2 or 2, it means at time 2 or at 30 seconds. And then if we put a 0 there, that indicates the initial concentration at the very beginning of the reaction before the reaction has started. So we'll see those. We're going to see a lot of those subscripts tend to mean a certain special condition for whatever the subscript is of. So if we talk about just, again, defining rates, rates in general are a change in something per change in time. So a change in Y, some variable, some substance, something, in this case, amount of products or amount of reactants over a specific period of time. So typically rates can be calculated kind of like we do in math class with a slope. So y2 minus y1, what was the final value, what was the initial value, over what was the final time minus the initial time, the time duration. So a couple things that we should know. One, and I kind of gave this example just kind of like looking at, like, if I talked about making sandwiches. At some time, we might start with a full loaf of bread, and we're going to make sandwiches. Ignore the cheese for right now. So I have 24 slices of bread, but each bread requires 2 pieces of bread, makes 1 sandwich. So later on I have 22 pieces of bread, but I made 1 sandwich. And then I might have 20 pieces of bread because I used another 2, and now I have 2 sandwiches, etc., etc. So a couple things I want you to know. One is that for the reaction, that the reactants are decreasing, which means I'm going to have less at the end than I did at the beginning, which means I'm going to have a negative. If I just calculate the slope or the rate, it's going to be a negative number. Also, if there's a coefficient involved, it changes. It's going to be like a bigger number. So if I were to do the rate of bread consumption, maybe I do between, in the first 2 minutes, it'd be 20 minus 24, or negative 4 over 2 minus 0 over 2, which would be negative 2. But if I were to look at the production rate of the sandwiches, it's 2 minus 0 over 2 minus 0, and it's a positive 1. So one of the issues we have with defining rates of reaction is that I want to have one rate of reaction. It shouldn't matter whether I'm looking at how many sandwiches are made or how many pieces of bread were used up. They're in the same reaction. There should only be one rate of reaction. So I mean per reaction. So how do I deal with the fact of these coefficients? Also, I really don't care. I want all my values to be positive numbers. So when I talk about rate, I mean in a positive sense. So when I have these rates of reactants, they're going to be a negative if I don't compensate for it. And so that's going to play into our formula that I'm going to give you. All right, so when I talk about the production rate of a product, this is how much product I'm making over time. It will be a positive value. So I would be, how much do I have at the end? Concentration that I end up with minus the initial concentration I started with, which should be like 0 because I shouldn't have any products at the beginning, and then the time duration, delta T. And it would be positive, so if I just do this and I don't deal with the coefficient, I would call that a production rate. How much got produced? A consumption rate is what I would refer to for something that's a reactant. So if I have a reactant A and is being consumed, again, it would be a negative number if I don't account for it, but I want the rate to be positive. So I'm going to put a negative sign in front, and then I'm going to do the change in A over time. So how much do I end up with, which would be less than how much I started with, a negative number over the same time period, but the negative sign I put in front cancels out the negative change in concentration, so that overall the consumption rate will still be a positive number. Because I know it's being consumed. I'm not concerned about that sign. I want to make everything positive and not deal with signs. So we add a negative sign in there. So a production rate, I don't have to add a negative sign in front, but for a consumption rate, I do have to add a sign in front. And then these are just about a certain reactant or product. When I move and talk about the reaction rate, I now, in order to get them all to be the same, I now need to deal with that coefficient issue. So to account for the decrease versus increase, I will put a sign in front. If it's a reactant, I'll put a negative sign in front. And if it's a product, I'll leave it positive. And then to account for the different amounts of requirements of how many I need for the reaction to proceed or how many it makes, I'm going to divide by the coefficient of A. So a reaction rate is, again, I will use plus for products or negative for reactants, and it's 1 over the coefficient of whatever that substance is, and then the change in concentration of that substance over the change in time. And so this is typically how it's noted, but I sometimes find stepping through that first makes a little more sense. I usually, it's usually written as, for the reaction AA plus BP makes CC plus DD, the rate is equal to negative 1 over A, so negative because A is a reactant, and the coefficient is A, so I'll divide by A, times the change in A over the change in concentration of A over the change in T. Or, if I were going to talk about B, it would be negative 1 over B times the change in concentration of B over the change in time. Or if I'm talking about C, it'd be a positive 1 over C times the change in concentration of C over the change in concentration, change in time. And same thing with D. So it's typically written that way. Note that without the coefficient, these two, if I ignore the dividing by A and B, these would be the consumption rates of A or a B, and these two are referring to production rates. So with the production and the consumption rate, I don't have the coefficient involved, but with the reaction rate, I do. I hope that helps. So if I know any one of these, I can find the reaction rate. If I know the reaction rate, I can also find the consumption or the production rate of another substance in the chemical reaction. So I have these all set equal to each other so that I could convert from talking about one substance to talking about another substance or talking about the whole reaction. Just briefly talking about, let's kind of go to theory. The collision model. What happens in a chemical reaction? And why would that affect how things change? Let me just take my picture off of here. All right, so factors that we would observe would increase the rate of reaction. The idea is that we've observed that if you increase the concentration of a reactant, then the reaction is going to speed up. It's going to run faster. If you increase the temperature, the rate of the reaction is going to increase. If you have heterogeneous reactions, that means there's two states, like a solid with a liquid, increasing the solid surface area is going to increase the reaction rate. And also, just because we say increase or decrease, in different reactions, they're going to increase and decrease by different amounts. So if we want to kind of like, all right, where do those, why is that true? We can kind of explain them by this theory that molecules react when they have an effective collision. So I have two reactants are going to collide, hit each other, and if it's an effective collision, then they will react. So at increased concentration, I have a greater density of reactants, so they're more likely that two are going to collide. They're closer together. So I would expect that increase in the concentration, it makes sense that I would have a higher reaction rate. If I increase the temperature has to do with how fast the molecules are moving. The absolute temperature relates to the average kinetic energy of the particles, and so at higher temperatures they're moving faster. If they're moving faster, they're more likely to have a collision, so that's going to increase the rate. Depending on the shape and size of the molecule, the orientation of the collision, if like they have to collide in such a way that the two parts of the two big molecules are actually going to interact, and so sometimes that can have the likelihood of whether they're close enough to form bonds. And so sometimes, as far as an effective collision, it depends on orientation or the shape and how they collide. As far as the heterogeneous reactions, since liquids can only react with solids at the surface, the more surface area I have, there can be more collisions between the liquid molecules and the solid reactant. Like it can only take place at that interface, and that's why surface area has a factor. Okay, so average versus instantaneous rate. So now there's two ways I can measure the rate. I can measure an average rate, and turns out this is kind of an easy thing. It's like over some medium or a long duration of time, on average, what was the rate? So I'm not looking at like how it's changing with time. I just want to know generally about what was the rate. So in an average rate, this is over a long duration of time, I'm going to use the slope method. So I can use a slope formula to calculate the average rate. So it's the concentration of the final concentration minus the initial concentration on top divided by the final time minus the initial time. And so that would be how I calculate an average rate. An instantaneous rate is over a very tiny period of time. I'm like, right now, what is the rate? Okay, now right now, what is the rate? So it might change over time. And in fact, kinetics is all about how is the instantaneous rate changing over the course of the reaction and as a factor of what is the concentration of the reactants. Because that time period is so small, TF, TI are so close together, we can use a method in which we just sort of say, all right, we're going to use two close points, like the point just after, the point just before the point we're interested in, and get an approximation. We call that the difference method. But another way to do it is that we're going to borrow something from calculus. In calculus, it turns out that the slope of a point on a curve is the slope of the line that's tangent to that point at that curve. Remember, in a tangent line, when we draw a tangent to a curve, the tangent line kisses the curve at one point only. It only touches the curve at one point. It doesn't cross the curve at all. And so if we draw a tangent line and then we take a slope of that line, that would be the instantaneous rate at that point that the tangent line kisses the curve. So if we want to do an instantaneous rate, I have to graph it, and then I'm going to have to draw a tangent line at the time point that I want to know the instantaneous rate. And then I'm going to find 2 points on that tangent line, and I can do the slope method, y2 minus y1 over x2 minus x1. It's also true, and I probably should edit the notes to include, another way I can do something close to this is I just take, instead of doing a tangent line, I can also do, it's not as good of a method, but I can choose y2 and y1 and x2, x1, two points that are really close just before, just after the point of interest. That's called the difference method. It's not as accurate, but it usually gets me a pretty close estimation of the instantaneous rate. But when I'm asking you for instantaneous rate, we're going to draw a line. Or it might be drawn for you, and you just have to find 2 points on that line and determine the slope. Let's give you an example. So if I were looking for the average consumption rate of A between 1 and 3.2 seconds, I would look on the curve at 3.2 seconds and see that that's like 0.03 molarity. And then I would look at the time at 1 second, and I would go to the curve, and I would read off the point, so that looks like it's about 0.18 molarity. So then I'm, using the final would be 0.03 minus the initial, but remember, because it's a consumption rate, I put the negative sign in front so that it becomes positive. And then 3.2 over 1.0, I end up with 0.068. And my units would be molarity per second. If I wanted an instantaneous consumption rate of A at 1.5 seconds, I would go to 1.5 seconds. I would draw a tangent to the curve. Notice this blue line is just kissing it at the point, and it just touches at the 1.5 second point. And now I'm going to choose 2 points on this curve, on this blue line. So I've chosen 0.1 at 1 seconds. Note that now instead of being 0.18 where the curve is, I'm looking for the blue line, it's 0.17. And if I look at 2 seconds, it's a little bit above this line. So instead of being 0.15, it's like 0.17, I estimated, 0.17 molarity. Or no, so this one's 0.073. Yeah, so let's see. At 2 seconds, if I go up here, it's like a little bit above this line. So this is 0.07, but it's a little bit above it. So I said 0.073. So 0.073 minus 0.17, again, I use the negative sign because it's a consumption rate. I want to offset and make sure it's positive. And then the second time is 2 seconds minus the first time is 1 second. I'd end up with 0.097 molarity per second.